Now we're ready to talk about rate law. We're going to go beyond the definition. The rate law will show how concentration affects the rate of the reaction, and the rate law can include any of the reactants, maybe not all of the reactants, sometimes none of the reactants, and occasionally products. We'll very rarely see the products show up, but it is possible. So if a product shows up, I don't want you to be surprised by that. So when we are writing rate laws, I'm going to give you the generic version, but the products, you can see the products show up so rarely that when we do a generic reaction, we just say A plus B is turning into products. And the rate law is this lowercase fancy k times the concentration of A to the m power times the concentration of B to the n power. K is the rate constant. Now, we're going to have to find that from the data, but it is a constant that depends on how that reaction is running under what conditions at that moment. And then M, this is the order with respect to A, and N is the order with respect to B, and M and N are not the coefficients in front of A and B in the reaction. Sometimes you will be asked to determine the overall order of a reaction. If you have A and B, that the rate depends on both of those concentrations, then you would just add up those exponents to get the overall order. I have this in like capitals, lots of underlines. The rate law absolutely must be determined experimentally. You have to collect experimental data to determine and support your rate law. We won't be able to get it directly from the equation. So, what does this tell us? It tells us how the rate depends on concentration. So, what does a concentration dependency mean? And we're going to look at what this means through some examples. So the way that this experiment works, the experiment is called the method of initial rates. This is how rate laws are determined. If you're taking the lab class, you will do this method. So you'll run reactions and calculate their initial rates and use it to determine the rate law. So method of initial rates. So the rate initially, you look at the initial rate of reaction for several iterations and see how the rate changes as the concentrations change. So I'm going to give you this table for 2NO plus O2 turning into 2NO2. I've got 3 trials worth of data. In trial 1, my initial NO concentration was 0.010 molar. My initial O2 concentration was 0.010 molar. And when I measured my reaction rate, it was 1 times 10 to the minus 6th molarity per second. When NO was 0.01 molar and O2 was 0.005 molar, my reaction rate was 0.5 times 10 to the minus 6th molarity per second. And when NO was 0.005 molar and O2 was 0.010 molar, my reaction rate was 2.5 times 10 to the minus 7th molarity per second. So I'm going to compare these 2 trials. You'll compare trials where one thing is constant, right? So we have 2 reactants. We're going to isolate the change to just one of them and see how the rate is affected. So for trials 1 and 2, my NO concentration doesn't change. My O2 concentration changes, and my reaction rate changed. Now, the amount by which it changed, we're going to get into all of that. This is just what does it mean to have a concentration dependence. It means that when the initial concentration of something is changed, the rate of the reaction changes in those initial seconds that we're measuring. So compare trials 1 and 3. Now NO is changing. In trial 1, it's 0.010. In trial 3, it's 0.005. But the O2 concentration is the same for both. So the only thing that changes is NO, and my reaction rate changed. So the rate of this reaction depends on the concentration of NO and the concentration of O2. So whatever the exponents end up being, right, the M and N, the order with respect to each of these, right, we're going to look at how to figure all of that out. In my rate law, I will see NO and O2 based on this data, because when I changed either of them independently, the rate of the reaction changed. So some common dependencies that you will encounter as we do this, when M or N is equal to 0, this is a 0 order reaction or a 0 order dependency. That means no dependence, right? If you put concentration of A to the 0 power, you just get 1 out of it. So you can change the concentration, but the rate will not change. M or N equal to 1, this is first order, means the rate is directly proportional to the concentration, well, to the first power, but we can leave the first power off. It's just a directly proportional. M or N equals to 2 is second order. The rate is directly proportional to the concentration of A squared. So you will see the square show up in that dependence. You can have other orders, including fractions. So you could have M or N equal to 3, 4, 3 halves, 1/3, -2. Right. The negative means it's in the denominator, so it's probably a product. 0, 1, and 2 are the most common. I will give you data usually that is 0, 1, or 2, but especially when we do things like mechanisms later on, you will probably see these other dependencies come up. Okay, so let's look at some data with examples. For my generic reaction A turning into products, if I have 3 trials where I'm changing the concentration of A and looking at the initial rate, for this tabulated data, my concentration of A is 0.1, then 0.2, then 0.4 molar. The initial rate of this reaction in every case is 0.015 molarity per second. This is an example of 0 order. There's no dependency on the concentration. The rate is constant regardless of the initial concentration. So in my rate law, the rate is equal to the rate constant times the concentration of A to whatever the dependency is. Well, that's 0. So my rate is constant and the rate is equal to the rate constant. So you could find the rate constant for this reaction really quite easily because we know the rate. All right, let's look at a new reaction, A turning into products. And the data that I have here for you, trial 1, concentration of A is 0.1 molar. The initial rate is 0.015. When the concentration is 0.2 molar, the initial rate is 0.030. And when the initial concentration is 0.4 molar, the initial rate is 0.060. So let's compare these trials and figure out the dependency. So comparing trials 1 and 2, when you double the concentration of A, the rate doubles. 2 and 3, when you double the concentration of A, the rate doubles. I just started at a higher point. We could also compare 1 and 3. From 1 to 3, I have quadrupled my concentration of A and my rate quadrupled. So whatever I do to A, it does the same thing to the rate. This is a rate directly proportional to the concentration of A. This is a first order dependency. So my rate is the rate constant times the concentration of A to the first power, which we could just leave the first power off. Now you can, there's kind of the writing out the words, this is kind of an intuitive way. You could do this in a more mathematical way if you prefer. So from trial 1, my rate is K times the concentration of A to the n power, whatever n ends up being. From when I compare this to trial 2, if I look at the rate value in trial 2, it's 2 times the rate value from trial 1. So I can say 2 times the rate equals the rate constant, and then I got here by doubling my concentration. So in brackets, I can say 2 times the concentration of A, all to the n power. So this will happen, right? If you double the concentration of A, you will get a double rate only if n equals 1. All right, another new reaction, new starting point. Let's look at this data. Trial 1, A is 0.1 molar. Trial 2, A is 0.2. Trial 3, A is 0.4. My initial rates for trial 1, it's 0.015. For trial 2, it's 0.060. And for trial 3, it's 0.240. So let's compare trials 1 and 2. When I double my concentration, my rate is quadrupled. So from trial 1, my rate is equal to the rate constant times the concentration of A to the n power. In trial 2, my rate is 4 times what it was for trial 1. So 4 times the rate equals the rate constant times 2 times the concentration of A, because I doubled my concentration, to the n power. So this can only be true, right? The only way that this works, 2 to the n power is equal to 4 when n is equal to 2. So this is a second order dependency on the concentration of A, and it makes my rate law, the rate equals K times the concentration of A squared.